In this video, we will talk about inverse functions. Inverse functions are basically undoing what the other one does. So given f of x is equal to 2x, if we have an input of 3 as an x, so then we have 2 times 3, so the output is equal to 6. Inverse function is if we plug in 6, with what kind of operation will we get 3? Obviously, this has to be half. Half of x will return the value of what we started with, right? So instead of multiplying by 2, you want to divide it by 2. In other words, you want to multiply by half. Couple things to keep in mind when we're looking for an inverse function. Inverse function must be a function, so that means it needs to pass a vertical line test. Inverse function is a reflection of f of x in the line y is equal to x. That means if you have a function that looks like this, which is an f of x, it must be a reflection on the y is equal to x. Y is equal to x is a straight line, a linear function that passes on to the origin. So it must be a reflection. That means if you fold onto this blue line, all the values must match. So must look like this. So that one would be an inverse of x. The last one is f of f inverse of x is equal to x, and f inverse of f of x is equal to x. What does that mean? So let's look at the second one here. If we have f, the function, which maps from x to y, then we know that inverse of that function will map everything from y to x. So if we are looking at the second composite function where f inverse of f of x is equal to the f of x has a value of y, right? So some kind of element that's in big Y. So we're going to let that be small y. So f inverse of a small y, but if you look at f inverse, right, that small y is an element from a big Y, which maps it onto an x. So that must be true. So can you also solve for the first case why that must be true? Given f of x is equal to 2x plus 3, find the inverse and graph both of these graphs. So we talked about in the previous video that if you're given a function, the inverse function is an x and y being switched. So rewrite this function that's given, y is equal to 2x plus 3. Then second, switch x and y. X is equal to 2y plus 3. Then solve for y. So we have x minus 3 is equal to 2y. X minus 3 over 2 is equal to y. So your inverse function is equal to x minus 3 over 2. So let's write down the steps. So rewrite as a y is equal to second, switch x and y. Third, solve for y. And then 4, rewrite in terms of x, but the inverse of x. Let's then graph these two functions. The first original function is 2x plus 3, has on y-intercept at 3. So 1, 2, 3. That's where it's going to pass the y-axis. And then it has a slope of 2, which means it rises to over 1, right? In other words, it goes down 1 and left to 1. And the zeros are going to be 2x plus 3 is equal to 0, right? So then x must be negative 3 over 2. So at x equals to negative 1/2, that's where my 0 is going to be. So that is the graph of f of x. Right. Now let's graph the inverse function. The inverse function is equal to x over 2 minus 3 over 2. So that means the y-intercept is at negative 3 over 2. So 1, 2, in between 1 and 2. And the slope is 1 over 2. That means it's rising 1 over to 2. So that must be over here. Rise 1 over to 2, so must be over here. Therefore, the graph of this inverse function will look something like this. Alright, let's just double check that's where it crosses the x-axis. So if it's crossing the x-axis, the y value must be 0. So that means 0 is equal to x over 2 minus 3 over 2. So that means 3 over 2 is equal to x over 2. Multiply 2 on both sides, x is equal to 3. So yes, that's correct. Alright, now let's compare the coordinates on here. In the original graph, we had 0 and 3. On the inverse function, which is in blue, no, the purple, the inverse function, let's label this inverse function. The coordinate of 0 and 3 became 3 and 0, right? And we already talked about the x-intercept on both of these cases. This one over here had a coordinate of negative 3 over 2 and 0. And that was also true when it was a 0, negative 3 over 2. So you notice in here that the y-intercept becomes an x-intercept, x-intercept becomes a y-intercept on the inverse function, and the remaining of the coordinates on these points, the x and y values are switched on the inverse function. Given y is equal to x squared, find the inverse function by graphing. So in order to draw an inverse, it must be reflected on the line of y is equal to x. So pause this video and see if you can do this. Alright, so once you graph the inverse function, it should look somewhat similar to this, right? So that is the inverse function of the given function. Interestingly, is this a function? Does it pass a vertical line test? No, it doesn't. So this is not an inverse function. In order to make this an inverse function, if we restricted the domain on here, instead of y is equal to x squared, where x is all real numbers, if we restricted the domain as the x greater than or equal to 0, so we would have a graph to start with that's just half of that. And if we can reflect that onto y is equal to x, we would get a graph that looks like this. Then it would be an inverse function. So just keep in mind, when you're looking for an inverse, that inverse must be a function. Self-inverse function is symmetrical about y is equal to x. So what are some functions that we already know that are self-inverse? Y is equal to 1 over x. We know that graph of that looks like little butterflies. Then if we plot the line of y is equal to x, right? So then this part is symmetrical about this. This is symmetrical on here, so therefore this is an example of a self-inverse.